In this video, we will be solving paper 1 questions for topic 11, electromagnetic induction. The first question asks, what is capacitance? Capacitance of a capacitor is defined as A, the ability to store electrical charge, B, ratio of charge stored to potential difference, C says ratio of potential difference to charge stored, and D says ratio of work done to charge stored. So capacitance is equal to charge over potential difference. So B is the answer. C is wrong because the ratio of potential difference to charge stored is equal to electric field. And D is wrong because the ratio of work done to charge stored is equal to potential difference. A battery is used to charge a capacitor fully through a resistor of resistance R. The energy supplied by the battery is E sub B. The energy stored by the capacitor is E sub C. What is the relation between E sub B and E sub C? So we have a RC circuit, and both of them are connected to a battery. When the capacitor is fully charged, current is equal to 0. So the potential difference of the resistor is equal to 0, which means that the resistor is basically a wire. So the circuit can be simplified to something like this. So the resistor becomes a wire, and the capacitor is connected to the battery. Right. So by loop rule, we know that the sum of potential difference across the circuit must be 0, which means that the potential difference of the battery is equal to the potential difference of the capacitor. So now we want to know the energy stored by the capacitor and the energy stored by the battery. The energy stored by the battery is equal to potential difference across the battery multiplied by total charge in the circuit. The energy stored by the capacitor is equal to a half multiplied by capacitance multiplied by the square of the potential difference across the capacitor. And because the potential difference of the capacitor is equal to the potential difference of the battery, the equation becomes a half multiplied by C multiplied by the voltage of battery squared. And we know that charge, let me say this, capacitance multiplied by potential difference is equal to charge. So this is gonna give me total charge in the circuit. Then the expression for the energy stored by the capacitor becomes a half multiplied by the total charge multiplied by the potential difference. And from the two expressions, we can see that the energy stored by the capacitor is only a half of the energy stored by the battery. So energy stored by the capacitor is less than energy stored by the battery. C is the solution. A alternating circuit is sinusoidal and has a maximum value of 1.5 ampere. What is the appropriate value of the root mean square RMS current? So we have a maximum current of 1.5 ampere, and we know that the average current, or the RMS current, is equal to 1.5 divided by the square root of 2. this is the definition of RMS value. So RMS value is equal to like the maximum volume, not volume, but value. So maximum value divided by the square root of 2, which gives us something close to 1. So C is the answer. When solving the problem, we can directly eliminate A and B because they're larger. Because the RMS value cannot be larger or equal to the maximum value. So A and B are definitely wrong. For D, we can see 0.75 ampere is equal to a half multiplied by 1.5. And this is way too small, right? So C is the only possible answer. A magnetic field of strength B links a coil. The direction of the field is normal to the plane of the coil. The graph shows how B varies with time t. Which of the following shows how the induced current ellipson in the coil varies with time t? And here are the graphs. So how do we solve this problem? We know that induced EMF is equal to negative n, where n is the number of coil, multiplied by the rate of magnetic flux, the rate of change of magnetic flux. And magnetic flux is equal to magnetic field multiplied by area. The area remains constant, so the expression becomes n multiplied by A multiplied by dB over dt. And we have a graph of B versus T. So basically this term here is the slope of the graph for B versus time, which is given by the graph right here. So we see that here they have a constant slope. Here they have a constant slope. Here they have constant slope. Here they have a constant slope. So the induced current is gonna be a constant, right? So the induced current is equal to negative n multiplied by A multiplied by the slope of the graph. And for the slope here, we have a positive slope. So for 1, we have a positive slope, but we have a negative sign here. So induced voltage is gonna be negative, and it's gonna be constant. So D is the only possible answer. We don't really need to see why here is negative. You don't even have to go this detail. As long as you can see that the slope of the graph is constant, the slope for B versus time is constant, you know that the expression here gotta be a constant. So A, B, C are immediately wrong. You can check your answer using the expression here, like check the sign, to just help yourself to have a better understanding of what induced EMF is. Which of the following experiments provide evidence for the existence of matter waves? A says the scattering of alpha particles. This is wrong because the scattering of alpha particles shows the existence of proton. Right? Electron diffraction is the answer. By doing the experiment, it basically shows the wave properties of particles. so it shows the existence of matter waves. C is wrong. Gamma decay shows the emission of photon as energy. So basically, when electron absorb photon, they go to a higher energy state, and when they emit photon, they release energy, so they go to a lower energy state. So this is related to photon. Photoelectric effect is also wrong. So photoelectric effect is a phenomenon in which when light shines on a metal surface, electrons are injected from it. It provides evidence to show that light is quantized, meaning that they are an integer multiple of something. So D is also wrong. D shows light is quantized. Three identical capacitors, each of capacitance C, are connected as shown. What is the total capacitance of the combination? So there are two possibilities for capacitance combination. One is in parallel, and one is in series. When capacitors are connected in parallel, the total capacitance is equal to the sum of each individual capacitance. So C parallel is equal to C1 plus C2 plus Cn. When capacitance are connected in series, the total capacitance is equal to this. So they're opposite to resistors. For this problem, we have three capacitors. Those two capacitors are connected in series. So the total capacitance for those two capacitors is equal to, let me call them just C series, is equal to 1 over C plus 1 over C, which is equal to 2 over C. So the total capacitance is equal to C over 2. And then the circuit simplified to something like this. And the total capacitance here is equal to, so C parallel, we add up each individual capacitance, is equal to a half C plus C, which is equal to 3 over 2C. So C is the answer. A capacitor is charged by a constant current of 2.5 microampere for 100 seconds. As a result, the potential difference across the capacitor increases by 5 volts. What is the capacitance of the capacitor? So we have current here, we also have time, and we have voltage. When the problem asks us to find capacitance, you should immediately know that capacitance is equal to charge over potential difference. Like, this is how capacitance is defined. And charge is equal to current multiplied by time. So now we can substitute numbers. Current is equal to 2.5 microampere. Converting microamperes to ampere, we multiply the quantity by 10 to the power of -6. And then time is 100 seconds. Potential difference is 5 volts. So this gives us 0.5 multiplied by 10 to the power of negative 6 multiplied by 100, so 10 to the power of 2. And capacitance has a unit of farad. Simplifying the answer, we got 0.5 multiplied by 10 to the power of negative 4. And this gives us 50 multiplied by 10 to the power of negative 6, which is equal to 50 microfarad. So D is the answer. When converting unit, just remember that micro something means 10 to the power of negative 6. Like this is a prefix for unit. You have like milli, micro, and it's helpful to know them. An alternating current generator produces a RMS ENM of ellipson at a frequency f. The rotational speed of the coil in the generator is doubled. Which of the following correctly identifies the new input RMS EMF and the new frequency? So we have a AC generator, and when you see AC generator, you should immediately know that the ENM refers to the induced current. Induced ENM. And induced voltage is equal to negative N multiplied by the rate of change of magnetic flux. And magnetic flux is equal to magnetic field multiplied by area multiplied by cosine omega t, where omega refers to like angular velocity of rotation. So differentiating everything, we get induced voltage is equal to negative NA. The derivative of cosine is sine. So sine omega t, and then multiply by omega. Right. And then the negative sign cancel out because the derivative of cosine is negative sine. So negative become positive. This gives us NA omega sine omega t. So when frequency is doubled, Sorry. So when the rotational speed is doubled, so omega is doubled, induced voltage is doubled. So it's gonna be 2 ellipson. So B is wrong, D is wrong. And we know that angular frequency is equal to 2 pi f. So when angular frequency or the rotational speed is doubled, f is doubled. So A is the answer. The takeaway of this problem is to know induced voltage is directly proportional to is directly proportional to rotational speed. I'm not really sure if you need to know this part, like how to take derivative, as IB doesn't require like our physics HL student to take AAHL, but I think it's helpful to know how to derive everything, as you probably know some calculus. And also like this equation here is also very helpful. So angular velocity or rotational speed, depending on the context of the problem, is directly proportional to frequency f. The voltage output of a particular power station is stepped up by a factor of 1000. As a result, the power loss in the transmission cables is reduced by a factor of what? So power in a circuit is equal to voltage multiplied by current. And the voltage output is stepped up by a factor of 1000. So how do we find the reduction in power loss? Well, we know that power is equal to voltage multiplied by current, and this is equal to voltage squared over resistance, because it is stepped up by a factor of 1000. The power loss is gonna be reduced by 1000 squared, which is 10 to the power of 6. So B is the answer. The reason why we don't use V multiplied by I here is because we are not sure how current will be changing when the voltage is being stepped up by a factor of 1000. But when we use V squared over R, we know that resistance is going to be a fixed value. Like it's not going to change regardless of how voltage change, because resistance is determined by conductivity, which is a property of the material we use. So by using this, we sort of filter out how the interaction between current and voltage, which helps us to get an accurate solution for this problem. An ideal transformer has a primary coil with N sub B terms and a secondary coil with N sub S terms. The electrical power input to the primary is P. Which of the following is the power output for the secondary? So the key term here is ideal. For an ideal transformer, the efficiency is gonna be 100%. So the electrical power produced by the primary is equal to the electrical power produced by the secondary. So if the primary has a power of P, the secondary will also have a power of P. An aircraft with a wingspan of 50 miles horizontally with a speed 200 meters per second. The vertical component of Earth's magnetic field at the plane's position is 10 microtelsa. What electromotive force is induced between points A and B on the aircraft? So we know length, we know speed, we also know magnetic field, and we need to find EMF. How can we do this? So I think in the formula data booklet, you have a formula for motional an electromotive force, which is given by this. So induced voltage is equal to B LV. So substituting everything, we get 10 microtausa. Again, convert to tausa. We multiply the quantity by 10 to the power of -6. And then the length is 50 meter. Velocity is 200 meter per second. Simplify everything, we get 0.1 volt. So the answer is A. The algebra can be a bit tedious, but just try to be careful with algebra, and everything else should be pretty straightforward. 3 capacitors, each one with a capacitance C, are connected such that their combined capacitance is 1.5 C. How are they connected? So we know the total capacitance. We only need to calculate the capacitance for each combination to see which option is correct. Recall that the total capacitance for a parallel combination is given by the sum of each individual capacitance. So C parallel is equal to C1 plus C2 plus Cn. And for capacitors in series, 1 over their total capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over Cn. Using these two equations, we can calculate the total capacitance for each option. So A, capacitors are connected in series. So 1 over the total capacitance is equal to 1 over C plus 1 over C plus 1 over C, which is equal to 3 over C, giving us a total capacitance of C over 3. For B, the 3 capacitors are connected in parallel. So the total capacitance is equal to C plus C plus C, which is 3C. For C, we have 2 capacitors connected in series. So the total capacitance for the 2 capacitors is given by 1 over C plus 1 over C, which is 2 over C, giving us a total capacitance of a half C. Then the circuit simplifies to something like this. And the total capacitance here is equal to a half C plus C, which is equal to 1.5 C. So C is the answer. Let's do D for practice. So we have 2 capacitors connected in parallel here. So the total capacitance is equal to 2C. Then the circuit simplifies to something like this. Where 2 capacitors are connected in series. So 1 over the total capacitance is equal to 1 over 2C plus 1 over C. And this is equal to 2C squared here, 3C. So 3 over 2C. The total capacitance is then equal to 2C over 3. The graph shows the power dissipated in a resistor of 100 ohm when connected to an AC power supply of root mean square voltage of 60 volt. What are the frequency of the AC power supply and the average power dissipated in the resistor? So we need to find the frequency first. We have a graph of power versus time. How do we find frequency? Here is the tricky thing. One common mistake people make is look at the graph and say, okay, the period is equal to 0.02 second. So frequency is gonna be equal to 50 hertz. This is wrong because when we calculate power, we take the square of current, so it's not possible for us to have a negative power, right? And this makes the way we calculate period a bit more tricky. So the way to understand this problem is to first think about the graph for current versus time. For an AC current, if I draw a graph of current versus time, I have something like this. So this is time, this is current. Actually, let me not write current. This is time. And the current looks something like this. And power is equal to current square multiplied by resistance. So when I graph power versus time, I will square current. So everything will be positive, and then I will multiply by resistance, and the amplitude of power will be scaled by a factor of R. More accurately, I should say the value of I squared is scaled by a factor of R. So the graph looks something like this, where everything becomes positive because we are taking the square of current. So now if you want to find if we want to find period, we see that the period of current versus time is given by this, which corresponds to the period of power. So the true period here is not 0.02, but 0.04. We need to consider like two little graph here because we are taking the square of current. Now we know the period, we can calculate frequency. Frequency is equal to 1 over period, so 1 over 0.04, which gives us 25 hertz. And we want to calculate the average power. So power is equal to V squared over R, where V is voltage and R is resistance. This gives us average power is equal to average value of voltage, which is RMS value over R. And we know that the RMS value of voltage is 60 volt. So 60 volt, 60 squared over resistance, which is 100. Calculating everything, we get let me simplify the algebra. The 0 cancel out here. So average power is equal to 36 watt. The solution is A. For the next problem, we want to reduce power loss in a transformer. How do we do this? So the first one says we can construct the core from a solid block of steel. The second choice says we can use a large diameter wire in coils. And the last choice says we can use wires of low resistivity. And which of them can reduce power loss? So when we use a metal conductor, it increases the efficiency of conduction, which reduces power loss. So this is definitely right. So conductor or metals reduce power loss. If we use a wire with a large diameter, what happens is resistance will decrease. So R is equal to resistivity multiplied by length L over area, and area is equal to pi R squared. R is radius, and radius is equal to a half multiplied by diameter. So when diameter increases, resistance decreases, so power loss will be reduced. For the last option, if we use a wire with a low resistivity, resistance increases, so power loss decreases. So the solution is D. A rectangular flat coil moves at constant speed through a uniform magnetic field. The direction of the field is into the plane of the paper. A copper sheet is suspended in a region of uniform magnetic field by an insulating wire connected to a horizontal support. The sheet is pulled to one side so that it is outside the region of the field, and then released. The uniform magnetic field is directed into the plane of the paper. Which of the following is true for both the direction of the induced current in the sheet and the change in amplitude of the oscillations of the sheet with time? Okay, so we have a uniform magnetic field directed into the plane. So something like this. So when the sheet moves closer, what's gonna happen? So we have magnetic field here. So when the sheet moves closer, we can see that some magnetic field, let me change the color. So magnetic field is going through the sheet. And when magnetic field is going through the sheet, magnetic flux is changing. So magnetic flux is changing. And by Lenz's law, we know that when there is a change in magnetic flux, there will be an induced voltage to oppose the change. So magnetic flux increases, we will have an induced voltage, an induced current to oppose the change. So in order to reduce the change, induced magnetic field will point out of the page, right? Because we have more magnetic field that's pointing into the page. In order to reduce how much changes is happening in our magnetic field, we are gonna have a induced magnetic field that's pointing out of the change to cancel the field that's pointing into the page. And using right-hand rule, induced current will point in counterclockwise direction. Okay. Similarly, when the sheet moves away, so when it moves away, what happens is magnetic flux acrossing the sheet decreases. So flux decreases. Then the induced magnetic flux will oppose the change. So it will point in the same direction as the field that is present here. So the induced magnetic field will point into the page. Using right-hand rule, induced current will point in the clockwise direction. So this tells us that the direction of induced current will change. So A and C is definitely wrong. Now we need to think about amplitude. So intuitively, it makes sense that there will be energy dissipation, which causes reduction in amplitude. But more rigorously, there's gonna be eddy current. And eddy current is basically energy dissipation, or eddy current causes energy dissipation. And what happens is when eddy currents are present, we are going to have damped oscillations, which causes amplitude to decrease. So B is the answer. Which loops have the largest induced electromotive force at the instant when the loops enter the magnetic field? So induced EMF is equal to negative N multiplied by the rate of change of magnetic flux. And magnetic flux is equal to magnetic field multiplied by area. So in order to find the largest induced voltage, we want to see like which loop has the largest area at the instant when exposed to the magnetic field. And how we do this is imagining we are moving the loop. And what's gonna be the area of each loop when they're first exposed to a magnetic field? So if I move the loop, it's gonna be something like this, this, and this. And then I continue to move the loop. They become something like this. Right. Let me erase the blue thing. So at the instance when each loop are exposed to magnetic field, I'm gonna draw a line to see which one has the largest area. And for simplicity, I'm gonna draw the loop here, just to make everything clear. So the area here is equal to the area here. I'm drawing another loop here because my drawing is horrible and I don't want to cause any confusion. So let me make everything clear. The area here is the area here. The area here is the area here. And from the graph, you can see that loop Z has the largest area. So loop Z will have the largest induced current. So A is the solution. I think a confusion students make is like Y and Z, they have the same area here. But this is not really right because like at the instance when each loop is first exposed to magnetic field, loop Z has a larger area. But at time when they are completely exposed to the magnetic field, loop Z and loop Y will have the same area exposed to magnetic field, and they might have same induced voltage. But for this problem, we are considering the area when each loop first exposed to magnetic field.